the y component and the z component, they're all vectors. So when you add these vectors together, you take the square root of their squares. And in this study, the z component was the component used. Now, solar flares, as seen here, are large quantities of X-rays released from the sun. They're mainly comprised of X-rays, but they also contain UV radiation and other parts of radiation seen at different wavelengths. CMEs, coronal mass ejections, are released from the sun, sometimes during solar flares, but sometimes not during solar flares, and sometimes during solar flares that aren't CMEs associated. But both events release a large amount of energy and relativistic particles into the Earth's space environment. So when they come into the Earth's space environment, they will cause interactions. Now, the solar flares are classified on GOES classification system. GOES stands for Geosynchronous Operational Environmental Satellite. It's run by NOAA. On this graph, we can see that there's an X6.9, M2.5, and M3.5. Well, what does that mean? It means this, that they're measured on the wavelength of 1 to 8 angstroms. And then the flares are classified on a scale of A, B, C, M, and X. A is the smallest, up to B, then C, then M, then X. So here, this is an event that can cause potential aurora in Michigan, in Nebraska, and in the lower 48 states. So the purpose of this project is to determine whether there's a correlation between the already used classification system for solar flares and whether they have an impact on the Earth's magnetic field, also called the geomagnetic field. The importance is it brings forth the question of whether or not there's a better system to classify solar flares than the X-ray flux that they give off. My hypothesis at the beginning was that there would be no correlation between the ghost flare classifications and the effect on the geomagnetic field. So one of the satellites used was the GOES satellite, and it has all 12 through 15 X-ray imagers attached. Time and intensity of solar X-ray events, and when they happen, are uploaded to a database on the graph you saw earlier. And this is GOES 15, which is the main satellite used for classifying flares. The 8th satellite, the Advanced Composition Explorer satellite, is located 1/100th the distance from the Earth to the Sun, at the L1 point where there's no gravity acting on it. Collects data on the interplanetary magnetic field, the solar wind velocity, and the density of particles in the solar wind. The solar wind is basically a less intense version of the solar flare. It's a constantly occurring event, and it will always be happening. And we occasionally get outbursts of solar wind that are not associated with solar flares. But the data from the 8th satellite is sent to an online database where I was able to download easily. And I used the 8th data and the THEMIS data, the time history of events and macroscale interactions with auroral substorms. They gave 11 schools magnetometers across the United States, 3 in Alaska, 8 in the lower 48. The data reported by magnetometers is sent to the University of California, Berkeley, where they host a website that you can download the data from. The data I used in my project was from the Remus, Michigan magnetometer, which is located behind the Mosaic School at my high school. And this is a event report from the Space Weather Prediction Center. They're put out by the Space Weather Prediction Center, and they're used to locate times of when flares occur on the sun. And when the flares occur on the sun, it takes approximately 8 to 9 minutes for the X-ray radiation to get to the Earth and reach the GOES 15 satellites. So, as we can see here, at 1:44 a.m. to 2:06 a.m., there was X2.2 flare. That is the flare that would be able to cause, once again, auroras down the lower 48. Now, the base data collected with the Advanced Composition Explorer, I use solar wind particle density, speed, and I have the BZ GSM position. The BZ GSM is basically it's the sun's magnetic field and the location that the sun's magnetic field is at, the polarity of it at the time. And that was downloaded for 72 hours after the event occurred. I download the BZ GSM, the proton density, and solar wind speed, and put it a date, and then download the data. Then, data for the strength of the BZ component was also downloaded from the THEMIS data collection website 72 hours after the flare occurred. The reason for 30 to 72 hours is because it takes 30 to 72 hours for solar flares effects to fully reach Earth, usually a CME, while it has protons and electrons that reach here in less than less than 15 minutes. Those generally do nothing to the magnetic field. While these accelerated protons can wreak havoc on infrastructure systems and other systems related to satellites and electronics throughout the Earth. Sometimes it can cause electric currents running through the ground, usually seen in Sweden and Norway and Finland. And this is another example. I just select Ramus, Michigan, select the start date, the end date, download data for up to 10 days at a time. So in order to measure the effect of solar flares and CMEs on the Earth's magnetic field, I had to create a new system, because currently the one we have in place is not really too well for this type of research. I call the system the geomagnetic variational intensity scale. It is the log of A divided by T when A is greater than 1. That is for when a solar flare or CME hits and reduces the strength of the magnetic field. And when it's a positive event, it's log of T divided by A, so it's to give us a positive number. When it's equal to 0, there's no change in the magnetic field. The GVIS is equal to 0. So A is equal to M with D, while M is the maximum strength of the field before the flare. And as we see here, we'll say the flare started right there. The magnetic field builds up strength, then it collapsed on itself. Then we took the end point, and to P, that was our D. It was the average of all points between those 2 points. And that was giving us our A. Then the T was the duration of the flare in seconds. P was the recovery point of the flare, so as close as it was to before the flare happened. There was one problem with the system, though. It's called diurnal variation. Right here, we see an effect of a solar flare. But right here, this is the effect of the sun just doing its daily duties. It's caused by ionosphere manipulation from the sun. When the sun shines on the day side of the Earth, it causes interference in the magnetic field. And when this happens, it shrinks the magnetic field at first, just like a solar flare would, then drastically drops the strength of the magnetic field throughout the day. Then once Earth turns away from the magnetic field, or turns away from the sun rather, it starts to go back up to its original level. So this would usually occur between 1200 and 2200 Universal Time daily in Ramus, Michigan. So this is still a unique problem for the GVIS, but as you can see in the data, it is separated so as to not prevent the problem.